Welcome to Academic Digest class. Today we are going to be continuing our class on integrated rate law. So I told you that for you to do anything on integrate on rate law or rate of reaction, there are four ways to express the equation: using differentiation, using integration, using half-life, and using isolation method. These are the four ways to express the equations of integration. But remember, we are still dealing with integrated rate laws. So come with me, let's go there. Remember that rate is directly proportional to concentration. This is the concentration box. Let's say this substance or the reactant or the product is, let's say in this case, B. And we are talking about first order. First order is when the power is 1 and anything on its own is raised to power 1. So introducing proportionality constant, I have K multiplying this concentration of B. So if I know this, I need to still remember that rate of reaction is defined as the change in concentration of reactant or product with time. And we also say that change of reaction or rate of reaction is the rate or the speed of disappearance of concentration. So that is why I have this negative sign. We normally use the part of reactant all over change in time. And this is equals to the principle which says that rate is equals directly proportional to concentration. If I know this, I need to do it in such a way that the concentration is one side, everything not concentration is on the other side, because I'm trying to derive an equation for concentration at a given time, not the initial concentration, but concentration at a given time. So doing that, I'll simply say anything standing on its own is over 1, cross multiply, I get minus D change in concentration of B is equals to K concentration of B dt. We divide both sides at this junction with concentration of B so that we can be able to get it on the left hand side. So we do this. You do this with me and God will bless you. All right. So at this junction, we can see that we now have K change in T on the right hand side, and on the left hand side we have change in B all over concentration. B change in concentration B all over concentration of B. So we need to make this subject of the formula, left hand side. So we need this to cross over. So we can say divide both sides by minus 1. This will cancel. Then here it will get stuck. So we have minus K delta T is equals to change in concentration of B all over concentration of B. So it's at this point we need to remember that anything, this thing now, this is the sentence as saying 1 over concentration of B with respect to B equals to minus K change in T. We introduce our integration sign, and this integration sign is such that we move from 0 to the upper boundary, 0 to the upper boundary. So whenever I'm integrating, the minute I introduce a integration sign, this now becomes integration of 1 over B with respect to change in B, with respect to B. This change becomes with respect to concentration, which is this box concentration B. So if I do that, I will notice that if I have, for example, 1 over X and I'm integrating it, this, okay, let me use B here. This is the sentence as saying B raised to power minus 1. Then integration says add 1 to the power, then divide by the whole power, minus 1 plus 1. Notice that what I have here, minus 1 plus 1 is B, concentration of B raised to power 0, all over 0. It is an abomination for 0 to be the denominator. In your mathematics, fundamental mathematics, they told you that whenever 0 is at the denominator, it's said to be undefined, or you say it is tending towards infinity. And the integral of infinity is simply taking the natural log. So what I just need to do is to simply say this is 1 over 0. And it's simply the sentence as say, instead of doing this to get 0, just do natural log And whenever I have anything 1 over b, or 1 over x, or 1 over a, or 1 over y, or 1 over c, or 1 over, which will end up giving me 0 as the denominator, I simply do natural log of that particular thing. So I will introduce the natural log. So what I will have here is simply natural log of concentration B. Now remember that what we are doing here now has a boundary. Don't come and tell me what of this one. Remember I said we are integrating this with respect to this. So, and since this is at the denominator, it's going to give me in such a way that we get the natural log of this. That's how we integrate it. So if I know that, I will have my boundary t and 0 equals to, I'm allowed to pull out the k one side, and then I have integral of dt, which there is an invisible one here. So this is going to give me minus kt, boundary t 0. So I have the sentence here. This one is going to be the sentence I'm saying, okay, let me rewrite it. So remember I told you that this is going to be the sentence that's saying ln B, concentration of B at T, minus ln concentration of B, initial concentration of B, equals to minus KT at T minus T at 0. So T is what we are dealing with here. T at T and T at 0. Notice that T at 0 is 0. So I just have minus KT equals to ln BT minus ln initial concentration of B. We always try to make that which is having a particular time to be the subject formula. At this point I've gotten what I need, but I just need to make the subject of the formula. I have ln natural log of concentration B at given time is equals to minus KT plus ln natural log of initial concentration. I always pull it this way. Some people can choose to put their own differently, but I always pull it this way so that if you look at it, you see that everything here can give me a straight line graph. Y is equals to, this is x, this is m, then this is c, which is intercept. So I always pull it this way so that if I want to plot the graph, I know what to do. I know how to plot the graph. You can solve this, and at the end of the day they tell you plot the graph. So I know what to do. That is that for the first order reaction. Now let's move to integrated rate law for second order reaction. So let's speed things up. So integrated rate law for second order reaction. I know I've solved video on third order and zero order. So for second order reaction, it simply means that if R is directly proportional to, let's say concentration here is Z, that means that R will be equals to KZ, and in this case Z will be raised to power 2 since it's second order. Remember I taught you that when I have let's say concentration like this and another concentration like this, the total concentration here 1 1, the total concentration here is 2 because this one has power 1, total concentration is 2. So check my video on rate of reaction, you understand better. So remember, this is rate of disappearance of concentration Z with respect to time is equals to KZ square. So we need to move everything Z to the left hand side, trying to make it sort of formula so that I have I believe you understand what I did. It's more like saying cross multiply, then divide both sides by this. For those of you that maths used to trouble, see what I did. I did So carry this come here, carry this come here, you have k z square dt is equals to minus dz. Then divide both sides by z square. I know some of you, once they do one small thing without listing the step, you get scared. So you see it. That is how we got this. That is how we got this. All right, now look at this. You now see that at this point we have minus. We say divide both sides by -1. Divide both sides by -1. This will cancel this, so that I now have d change in concentration of z all over concentration of z square is equals to minus k change in t. So at this point, I need to always remember to factor this out. Once I see the same thing up and down, and I know I want to do integration, I need to do 1 over square. Now dz is equals to minus k delta t. That is change in t. Now introducing the integral sign, introducing integration sign. Now I will now have integral from 0 to a particular time, from 0 to a particular time. So at this junction, I can say integrating this with respect to, once you introduce the integration sign, this becomes integrating this with respect to z. It's just like you are doing this and z is here. Assuming I have this here and I come and have t here, it can't work. Whatever I do, I will still need to find a way to call back this thing to become t. So but here is z and z, so I'm integrating this with respect to this. So I will now have, let's do it, 1 over z square is the same thing as saying z raised to power minus 2. That is concentration of z raised to power minus 2. And this is integration says add 1, then divide by the whole power. So this becomes -1 all over -1. And anything like this is the same thing as saying 1 over z. This the entire thing here is the same thing as saying 1 over z, and it's having -1. Now indices gave us that this is the same thing as saying 1 divided by z over -1. This is the same thing as saying 1 times -1 over z. This becomes -1 over z. So I will carry -1 over z and put here. That is the integral. That is the integral. So I will just have -1 over z. Then I will remember to put the immediately you integrate this thing, now you represent it with just the boundary equals to, then I can put this key, I can put this key outside, so that I have this thing is the same thing as saying minus k integral t 0 delta t. Now that I have this, if I do the integral, it's going to be the same thing as saying minus. In fact, when you are doing integration of rate law, just know that the right answer will always give you minus kt if you do things well. So notice that I have minus here, I have minus here, minus cancel minus. So I have 1 over z then equals to kt. Then remember the boundary. So this is the same thing as saying 1 over z. And remember that the z here is box. Remember, sorry, I forgot to put it. Remember that this thing we did here is the same thing as having our concentration. This represents concentration. We are not supposed to throw it away. It's always there. It's not just any z, but concentration of z. So all over z, the head, t. We always start with t, the upper boundary, minus 1 over concentration of z, initial. That is this t here. Here, initial. Equals to k, then t. This t will carry its own boundary, t and 0. And I told you that at, see what I mean, t at t minus t at 0. T at 0 will always be 0. Time at initial will always be 0. So I just have kt equals to 1 over concentration of zt minus 1 over concentration of z 0. That is initial equals to kt. So this is the same thing as saying 1 over concentration of z t is equals to kt plus 1 over concentration of initial Z. That is initial concentration of Z. So I can leave my answer like this. I can leave my answer like this. You understand? I can choose to leave my answer like this. Or I can still solve further. But the only thing is just that if you notice, this is the same thing as saying, this thing, everything here is the same thing as saying, watch, come in. Everything here is the same thing as saying concentration of Z, see, raised to the power minus 1, you can see it in textbook, is equals to KT plus initial concentration of Z raised to the power minus 1. That is indices. So this is also rigid. But this is how it's given. This is the final answer. This is how it's given. So, but you need to know this indices. You need to know this. So if I know this, I think to summarize it up for 0, first and second. For 0, first and second, I think if you really want to get the idea I need you to take when you are doing this is simply, for first order, you will always have, for 0 order, you always have lane A, that is AT is equals to KTE plus A, concentration of A, 0. Notice that's what we got at that point where we did 0 order. Yes, okay, yes, but just that it's carrying negative shaping. Yes, so this one is carrying negative. Then this is for 0 order. For 0 order. Now for first order, we will always have lane AT equals to, for first order, we always have lane AT equals to KT. I normally put KT plus, if you're able to know how we derive this, it won't be a problem. So before the concentration at a given time and concentration, initial concentration, you always have ln. Then let's check. You notice that we have minus again. We have minus again. So minus, you see? So this is for first order. First order. Just notice the difference. The difference is just that this one is having natural log. This one is not having it. Why for second order? For second order is just like everything here, but this time around is now having 1 over. So 1 over concentration of T is equals to KT plus 1 over initial concentration. But this time around, instead of minus, it will have plus. If you notice, for what we did here, the minus this side eliminated the minus this side, so then it will have plus. That's just the difference. So it will have plus. So this is for second order reaction, and this is what you will be taught in school, in your university. It's just that sometimes most of you want to see what of third order reaction. That's where we now have that one that has square roots. But you need to know that there's something we call molecularity. And molecularity simply looks at things in the context of, for example, if 2 people are fighting, you only see 3 people fighting. You understand? Even if 3 people are fighting, there is 2 persons majorly engaged in the fight. And if more than 3 persons are fighting, that's why in some cases we have molecularity for 3. That's why we have room. But you can never see fourth order reaction, because even if 4 people are fighting, they will have to divide themselves, 2 persons for each, respectively. So for the third order reaction, if you really want to see that, this is it. This is it. And I have a video on it. I have a video on third order reaction. So you check the channel how we derived this. But I know that using integration to derive rate laws is not hard. Using integration to derive it is not hard. Once you are able to remember this key step, that this is equals to this, and this is directly proportional to this, and raised to power this. So you just solve on. So please subscribe, like, and share. Thank you.